No, 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 no.
Howdy.
Howdy.
For all of you joining over Zoom, can you hear us?
No.
Awesome. So, howdy. I'm Jonathan. I'm the director of Igniters. Proud to welcome you all to our first preliminary design review for our rocket Thunderbolt.
And howdy, I'm Andrew, and I'm the project manager and chief engineer for my direct project. And I'm Eli's and the Price 5 plus 2028. Hey! And yeah, let's get into it. There's two QR codes here. We don't have a whole lot of time here, so if you have questions that don't really get asked, you can write them down. And we also have the PDR slide up if you want to review them as we go through. You can get a look at them.
Also, thank you all for being here, including those of you over Zoom.
Lovely. Okay, so this is just a brief breakdown of how the video is going to run. We're going to have introductions to basically a general overview of who we are, what we're trying to do with this, the dynamic structure, recovery, avionics, payload, propulsion, ground support, and some light conclusions. After each section, we'll have time for questions. Like I said before, we don't have a whole lot of time here, so any extra questions can be put into that Google form, and we'll answer them after. Yeah. So this is a brief introduction of our organization. None you kind of know just about this.
Yeah, so we're Igniters Rocketry. We are now completely and 100% on our own as an organization. We'll be official in less than a month. We have two areas. We have a project team. We have a mentorship group. Our mentorship group is doing their third and final flight of the program this weekend. And of course, you're already familiar with our project team.
So a lot of us were members of the previous project team who competed in IREC 2025. That did not go so great, to say the least. We got on the launch pad, we got the rail up, but we simply ran out of time to launch. With about 30 more minutes, we probably could have gotten it off the ground. It might not have been, so it's probably good that we didn't launch. We have a lot of experienced members now, multiple members having a lot of certifications, and yeah, we're gonna beat the hell out of competitions. So the competition we're competing in is called IREC, which is the International Archery Engineering Competition. IREC for short. We're competing in the commercial off-the-shelf category, POTS, which is you just basically buy everything commercially off the shelf. And our goal is to reach 10,000 feet, and yeah, it's not a big payload. So this is just a general flight profile. We'll see this again later in the slides. But there's the ignition and liftoff phase of the flight, the boost, coast. Then you reach apogee, and from apogee you have your grow deployment. You drift down to your main deployment, and then you have touchdown. We're looking at two potential test flight opportunities for Thunderbolt for the Lone Star Cup, and well, our flight might end up being a test flight. So hopefully not. But yeah. So this is kind of a breakdown of what you're looking at. If you all have the one page, you're kind of labeled on there as well. But from tip to tail, we have the nose cone, obviously. The forward section, which is the main parachute, is stored to the avionics bay, which is the avionics arm. And then the lower section, which is the throat parachute. Then there's a coupler connecting the lower section to the aft section. And then there's a tin can with the headphone. And we're going to break this down. A lot of this is going to be broken down a lot more. Again, it's just a brief overview of everything. Our loaded mass is 14 kilograms or 31 pounds. Our motor is the M1491, which has around 5,600 seconds of impulse in newton seconds, right? Our diameter is 4 inches, and we are at 129 inches long. Our apogee is just over 10,000 feet at 10,600, and our velocity is just over Mach 1. And our landing velocity is 22 feet per second. The livery is based off the German V2. It has high visibility with contrasts and colors. Looks great, in my opinion. The vehicle is named after the P-47 Thunderbolt and the A-10 Thunderbolt 2, both somewhat legendary and infamous aircraft. The stars and bars are U.S. Air Force insignia, and we're going to have X-10 written on the side and Thunderbolt, which is the name of the rocket. I don't assume there's any questions, but is there any questions what at all? Go ahead.
I have your format has like restrictions, like on the .eu.
Is that for the question?
Yeah.
Yeah. I will pick that demo. Thank you. Is there any other questions? So, all right, let's get right into it.
Howdy everyone, I'm Jace. I'm the Dynamics lead for Thunderbolt this year. We're using OpenRocket as our primary flight simulator. It's one, easy to design, a large list of real actual components to put masses where you want. It allows rapid iteration on design by pretty much any member who knows how to work the interface, and it's well proven. It's very popular. You know, it's pretty accurate and accurate enough for our purposes, at least. And our key figure is to take it from OpenRocket simulation. We're also using RasAero as a secondary simulator, has a better aerodynamic model, but no internal details. So it's being used primarily for validation. Here's key figures. Our velocity off the rail is 115.2 feet per second, which is like Mach 0.1. Our maximum velocity is 1,167 feet per second. Mach 1.05. And we're just barely crossing over the Mach barriers. We don't have to worry about aerodynamic heating or anything. Acceleration, we're getting about 19 Gs off the rail. Max Q 10.5 psi, and our apogee is 10,600 feet approximately. This is with a 6-degree launch angle. And here's just a graph of altitude over time. You can see apogee, ground contact, motor burnout, standard things. Here are our acceleration and velocity graphs. You can see this is of the first 27 seconds of flight or so. You can see our motor ignition and motor burnout. One thing about OpenRocket that I don't necessarily like is that it always says that acceleration is positive. So on the RasAero slide, which will be coming up soon, you'll see that right at really sharp corner, about 3 seconds for acceleration, it'll actually go negative because the rocket starts. And there's, RasAero altitude looks pretty much the same as the other one. And then here is RasAero acceleration and velocity. Acceleration on the top, velocity on the bottom. Again, as you can see, acceleration goes negative because the rocket accelerates. Here, before anybody says anything, we are overstable. I know we're overstable. We're going to, the reason we have it overstable right now is because, I'm sure some of you know, as a hybrid engine burns, its center of mass actually shifts rearward a bit before it starts shifting backward. And until we actually get our hands on the engine, we cannot figure out exactly how rearward it will shift. Current static margin, it would require a shift of over 12 inches to become unstable, which is way more than it's going to be. Like right now, we could knock probably 1.5 inches off the span of our fins with no real problems. Like I said, a breathing room design is taking span off the fin is easier than putting it up. And there's the graph of it. Again, this is incorrect as the engine file we have does not actually model oxidizer or mass flow batteries. It's just linearly interpolates between initial center of mass and final mass with some constant mass flow rate. And it will shift. It'll be brought down quite a bit. And 4 fins, got a little big 1/4 inch G10 fiber. Nothing terribly out of the ordinary there. Current fin thickness, material, shape, and flight conditions, we have a pretty significant margin of safety on fin flutter. And if we take this to span off, it'll just go even higher. So we do not expect to have any trouble with our current fin thickness. So any questions? Yes, please.
Back to the slide, the diagram.
Yeah. Back. Nope. Forward. There. Yes.
Span's already at 400, right?
Yeah. 4. Yeah. 4.
How much y'all willing to trim off that? Or your fitness? Based like span wise, it's already at pretty minimal 2:1.
Ratio or something.
It's generally about 1.25 pounders and span is like the bare minimum. One big bare minimum.
You could also just take one of the pins off too.
So to reiterate the questions,
Why not just wait till like why not just manufacture like that? That did the same thing once you get the or when you go.
Well, we will. This is just preliminary design until we actually figure out how much the center of mass to shift rearward by. We can't accurate the size of ends. Since I don't see much a whole bunch of design work until we figure out what we're actually designing for.
Place on the action manufacturing. That's what I thought you were saying. It should be.
Yeah, trimming off is a figure of speech thing. Okay. Like trimming off that, you're not actually cutting. You're just doing some marking.
So to clarify the question for the Zoom listeners, I know y'all can't hear. Basically, trimming the fins, little stitch, the general rule where you want your fins to be at least 1 caliber of span. In our caliber is 4 inches, and we're at 4.25 inches of span. So trimming it should was 4.5 inches of span. So trimming it is a little sketchy. But keep in mind we have 4 fins, and yeah, this will end up changing. The general shape will remain the same, but the span will likely decrease.
Leading edge and for the question, our leading edges, leading edge and trailing edge are both going to be hemispherical, or just round in general. Sorry, there's another question on Zoom there.
So the defect specified it cannot be over 18% stability margin before launch, and then during flight it cannot go over 25%. We're aware of that issue. Again, the issue is with our motor system. We don't have an understanding right now of how the center of mass of that system will move. So we're just wildly overstable right now.
Yeah, we're overstable so that we can make it less stable as we need to, because it's a little easier to remove fin and then have too much altitude, and then you change launch angle to get less. It's easier to get rid of altitude than it is to gain. So we have our fins too big for now.
So as we hone in our simulation and fix the current engine max issue, that stability margin will come within the detail and finished.
Yeah. Well, there aren't really any. They're in open-ended design problems. There are always a lot of ways to get something done. I'm just saying, we could reduce the span to just one sample. I also said we could go down to 1 or 2, 3 fins. Yeah, if we needed to, we could also probably, change the speed, we could do a whole bunch of stuff. An actual real drawbacks would have to be evaluated based on what we actually do with them. Any other questions? Yes, Casey.
What is this insurance?
Well, we're going to buy a G10 fiberglass sheet.
Well, like across the vehicle,
I believe it's currently all rough.
And we remember that setting, so don't have to worry. Yes.
Can you just go to the one slide real quick?
Yes.
I'm just got the. Is that just like an online resource that y'all have? Like it's online calculator?
So it's a online calculator that I've written and implemented into my 1 degree of freedom simulator, and it's very close to OpenRocket. And then I've also simulated it basically just like Excel little bits off the document.
And I guess, y'all just use the material form of the then. See.
Yes.
In relation to the bastion, have y'all reached out and figured out?
No comment.
We met with Paul and he gave us the proper method to simulate it, but that was a while ago. We weren't at that point where we were able to actually implement it yet. So we need to have another meeting with Paul so that he can refresh us on how to do it.
Is one of our number one concerns fixing the shifting mass of the motor.
Okay, there are no more questions. We are going to be moving on.
And remember, we have a question form, so if you have it in the top of your head, you can always write it down and submit it after the meeting.
Howdy. Howdy, my name's Sunny. I'm the lead for Igniters this year, so I'll be going over the dimensions of. Okay, to reiterate, this year we will be doing pods off commercial off the shelf. A lot of our airframes are going to be just bought, and our fins are going to be done by ourselves. We're going to be using SolidWorks to model our parts just to ensure that everything is going to fit together, and we'll use ANSYS to do FBA. Yeah, for FBA, I listed some of the analysis we'll be doing, mainly of buckling at max Q, the yielding of the internal structure at the main and row parachute deployment, and the hoop stress when our rocket is up at apogee. Okay, for our airframe, this is the dimensions we have. The diameters are pulled from Wildman, and our lengths are pulled from our open rocket file. So the forward section is going to be 26 inches long. Avionics bay is going to be 1 foot. Lower section is going to be also the complement or lower aft. It's going to be also 1 foot, and aft section is going to be 55 inches, and all of these are going to be box. Nose cone is also going to be bought from Wildman, 5:1 ratio Ogan. J length is 20 inches or full diameter sword. For our molded mount, we've decided to use Bluetooth, and Bluetooth is a very strong, durable material. It's also light, and we're gonna have 2 connections: one at the fin can, and one at the lower aft. For fin can, we're gonna go with G12 fiberglass again. And we're not so sure about the length right now. We're thinking about 16 inches. Again, outer and inner diameter are going to be pulled from Wildman, so the same as our airframe. One of the components, this will be our centering and bulkhead. We have to go with 4-inch birch plywood because it's just cheap, and we're just going to glue the layers together. As for like connection hardware, I bolts for the shock cord and parachute, share pins to pull the airframe together and help parachute deployment, and other low hardwares like nuts and washers to be distributed forces. And for the internal avionics bay structure, we decided to go with 4 1/4-inch steel blocks to secure our main parachute should point there. Fence, the dimensions are fence, we're gonna be using G10 fiberglass, span is 4.5 inches, roof cord is 10, sweep is 5, sweep length is 5 up. Thickness is gonna be a 1/4 inch and tip is gonna be 4 inches.
So we're gonna have G10 fiberglass fins, which will have a tip-to-tip fiberglass cloth reinforcement. There's a whole lot of details there, but we're gonna use 2 different types of fiberglass for primary reinforcing, 17-ounce biaxial, and then a 6-ounce fiberglass cloth, which goes on top, which gives it a nice finish. And then there'll be a 4-ounce fiberglass wrap around the leading edges. What you see there is the 10-can contraption from Thunderbolt, our IREX rocket from last year. And that is very similar to how this one will end up being. And we're going to be using US composites for all fiberglass technical.
Any questions?
Can you go to the bigger mount slide? What's the purpose of the one at the front?
Okay. So Casey asks, what's the purpose of the motor mount tube at the front? It's kind of just there. We could reduce mass by using just center rings up there. I'm sure that's what you're hinting at. Yeah. So that will probably end up being done. It's just this is how it was done last year and it works. It's the primary motivation. But yes, there's a very solid chance the motor mount tube at the top and the lower half coupler will be removed.
Everybody transfer that.
There's basically no point in it.
What's push for Bluetooth?
Bluetooth awesome. We could use a lighter material like craft phenolic paper or craft phenolic. But I would prefer more rugged material because, well, we don't necessarily have a place to store the stuff. And I'm afraid of things falling over and cracking and breaking and getting scuffed up.
There's just a small section of this.
That's true. Small section of fiberglass, but
Small section of Bluetooth cheaper than sugar.
yeah, but we don't ship it.
The primary mode transfer is a fine we this material we can choose.
Okay.
Any other questions?
On slide 24, just on the list of FDA, I was like, they'll have an argument that footer is going to count, but that's quite a bit sheer. If y'all are doing it CFD that, or even just y'all already have your plans, maybe just trying to get a basic estimate of what load is. Just trying to see if how much you want to be based on the actual bending, like the shearing thing, if you have an angle attack, right? So, because it won't just be like a axle, right? Or that's general. It's a vertical.
Yeah.
So are you saying use CFD or some other tool to basically analyze how much forces we're going to be having down there?
I mean, see the brute force, like I really want to get it. I mean, you can just do a basic, maximum, your pressure in your area, bend, right? So you can find like what that force is on the bend, and then apply it at the center of load of the bend. Be like, okay, this is how much it's going to bend. You know, you have your load, your position that would toward seeking, right? But yeah, I mean, the thing that I see that the cases that I see here are purely axial, rather than your greatest load case, which would be an angle attack, right?
Okay. So we'll be considering an angle attack for
I guess context, we usually like assume like 5 degrees.
it's the worst case.
But yeah, it's the decent.
Any questions?
We'll get this in question to the minute the laptop then.
I guess we'll move on for now, and we'll loop back to any questions at the moment.
Howdy. So my name is Evan Solis, and I'll be the recovery lead this year for our agri team. So just a basic like flight view of how the recovery will work. So basically, as right now, we have our go set at altitude, and it lows our feet deploy at around 12,000 feet. That number right now is still in the air as we get close to launch, where we will decide the actual altitude we would like to deploy our main specifically, since we know whether it's a big issue, trying to take it into account. So yeah. So first we talk about our growth parachute. This year we decided to go with a forward growth, specifically manufactured in Valkyrie. Right now we have this, right now we're 34-inch diameter throat, and yeah, it's right. So yeah, so of course the coefficient of drag is roughly 0.8 as listed on the website, and right now we have our descent rate for our roughly 2 feet per second. And yeah, like we'll be deploying this at 2. And then for our main parachute, we decided to go with the 72-inch diameter shadow floor elliptical parachute, also from Valkyrie as well. The coefficient of drag of that is roughly 1.6. It shares the same, similarities as 4-inch, but also have white stripes put into it. So as right now, we are considering doing this at 1,000 feet. Once again, that is subject to change depending on more conditions as we get close to launch. And yeah. So I went through and tried to calculate stat quality course. So basically, the way I put my stat course is just to maximum experience by the parachute, just stats open. Those numbers right now are a work in progress. I did a lot of cross on reference with some rocket forums as well as trying to calculate by hand, and also use other local guys. And yeah, these are the numbers I ended up letting on. So for the main, it's roughly 560 pounds. So on the trophy is 157. And for the opening force, I define that as the actual, force of the parachute after this, after that force as an opening. And for the main, I have roughly 115 pounds to the pounds. These assume the worst case scenarios, as well as I did not take into account any couple effects of the rocket itself. And yeah, once again, these are a work in progress. As we start getting a lot more defined numbers, I will be able to stop assuming less and being more precise, which I plan on doing, as well as taking into account other stuff. But yeah. So the core statement that we typically are going with this year is going to be a 1/4-inch tubular Kevlar. Right now that's also up in the air, but it has a 1,900-pound test strength. And yeah, it's the main purpose of it is to absorb the forces that keep the rocket connected. And yeah, so for our connection, we're going to go with quick links. Right now, once again, we are going with a 5/16-inch chain eye connector. It's rated for 1,760 pounds. And yeah, it's mainly we're going to be using that just to quickly attach the cords to our parachutes and just not struggle with us. So yeah, and then we're also going to be incorporating swivels, which is something that's new that we did not do last year. So this will help us ensure that our parachute does not tingle as it deploys, since it allows it to spin. And that's roughly rated at 1,500 pounds as well. And yeah, once we start getting a lot more defined numbers, you can scale a lot more down depending on what we need it for. Probably won't go down, probably will scale up. So and then of course we have to protect our parachutes. So we're going to be using Nomex sheet protectors, and the way the parachute protectors work is we're going to put the parachute inside of it. It's watered like a burrito. So that's the best way to describe that. And for our main rig, we want one that's 24-inch by 24-inch. Our goal is to be a 12 by 12. And yeah, once again, it's just to protect the parachutes with deployments. Of course, we're going to be using live powder charges, and they disperse heat, hot gases, which can be not good for the parachutes. So. And then we were considering going with a shoot back detector, the one that has the actual deployment bag, you can stick parachute in it. But we decided against it as of right now, considering the fact that we haven't used one, and considering our this is our second year of launch, we decided to go with like it again. That it will ensure a cleaner deployment and less points of failure. Yeah, so once again, I went through and calculated some shear pins as well as black powder. So for the shear pins, I calculated roughly 4 size number 4-40, which is rated at about 196.25 pounds to break them. Once again, this will be able to be scaled upwards or down depending on new numbers we end up calculating in the future. But right now, this is what it's going to go to with this current system we have. And then for black powder, you're going to be using black powder as separation charges. And as of right now, we're varying on the actual gram of amount of black powder we'll be using. Whenever I calculated the gram of black powder for the parachute we have right now, it was for our main, it was 3.5 grams as our main charge. And since we want to do for backup charges, I multiplied that by 1.25, giving roughly 5 grams. That's what I go for our main and for our growth. I calculated that at roughly 3. Once again, multiplied by 1.25, got 4 as a backup charge. And yeah, we will be testing these on the ground to ensure that it can also all the clean separations. We don't want to have any issues down the line, and it's also hard. So yeah. And then of course we will be testing all altimeters. We will be using our own homemade vacuum chamber for the necessary pressure testing. And yeah, this will just help ensure that the altimeter will be able to deploy the parachute at the correct altitude or side pressure differential that we actually needed to. And yeah, we're going to connect to some Christmas tree lights and have it deploy. So. Alrighty, go for it.
Go back to 41, please.
No,
Go back to 39 instead. Where do you intend on attaching the swivel along your line?
the swivels, we're going to connect it to our actual parachute strap lines, and we will be connecting that to a, that's still the kind of system we are going with that as well. Of course, that is something to change if anybody has better suggestions, but yeah.
In relation to that, the swivel would probably do best on the actual equipment on the collection, if that's where you can place rotation or at the equipment. Along with this link to the previously mentioned needing to save weight, have you all considered soft links?
I looked into it and decided to go to quick links, just considering that's I personally never use soft connections, but that is something we have considered, and as long as we do end up needing to lose weight, that is something that we'll really look into as well as consider using that as well. But as of right now, we've decided to go with the quick links themselves as a pre design.
We do have quite a bit of mass to kind of play around with. Our mass estimations for the internal component and hardware are quite a bit overestimated, to say the least. So there's room to play with that.
On your shock cords, 1,900 pounds seems like a lot, but depending on the reviewer, they're probably going to look at something more substantial than 1,900 pounds. We generally look at that 3,500 be absolutely.
All right, understood.
This will give you a heads up on that.
Yeah, I will definitely make a note of that. Right.
For your gross dash force, what horizontal velocity is that done with?
Can you repeat the question?
Your gross dash force, what horizontal velocity is that done?
Oh, I want to say I used terminal that's falling down. I don't know about horizontal terminal.
I think it was between 50 to 62%.
Yes, there you go. I don't know
For the horizontal one, I would suggest crashing 250 to 50. Just
per second?
Worst case, yeah, like add to your actual dose percent. Just because that's a nice worst case. So what was that? I think was here.
for the drone or
Your drone.
snatch opening.
Snatch.
I want to say about 157.
Yeah. So that's awfully close to your size.
That is also another thing that I did take into account. I do want to also have to scale it upwards. That is something I did get note of, but right now I decided to perform. But that is something I noted.
Yeah.
Yeah.
Are you all planning on having shadings on your journey sections to affect acceleration?
What second? Sorry.
On your actual journey, to prevent track acceleration.
I mean, if I'm being honest, I did, because I did consider, I took that into account with experience. So, yeah, but yeah.
To answer the question, there will be light shipments there. It's a slight chance.
Yeah, because when I read this, I did think that. Oh, any more questions?
Give it the very last like 20
What?
Like are you using trash cans or bulk tip or
They will be glove tip packed with science.
Yes, that is what we were going to do last night, right? Cool. Any more questions? Comments, concerns?
something? You want to answer the structure questions specifically?
Okay, so we missed the starter's question. Why do Bluetooth let out the rest of the rockets fiberglass? Casey also mentioned on that, I believe. It's looking like that will end up also being fiberglass, but also save shipping money by using the same manufacturer as our fiberglass, which are visibly just elevated back there. They're saving $12 in grants. So that will end up being fiberglass as well. Howdy. My name is Christopher Clem. I am the avionics and payload lead as well as the ground support lead, so you'll get to see my beautiful face up here another time. We are going to cover our avionics, and I've got a guest lecturer here, Jonathan.
I'm not official avionics Toby.
Yeah. And so in our rocket, we've got 3 independent systems. Technically 4. We'll get into it. So we've got a recovery, right, which is all COTS for right now. We're going to have an altimeter and a GPS system, just as per the DTAG. Again, we'll get into it. We've got an SRED flight computer. This is just essentially a similar thing to how we had it last year, where it's just a sensor array. It doesn't have any energetics hooked up to it yet. That's actually our last year's avionics section. And then it also had our altimeters and whatnot. But the sort of long-term goal with that is that we're going to try and fly this at IREX so that next year we can make something that actually has energetics hooked up to it. Finally, we have our payload, which is, the main payload of the rocket. And we'll talk more about that at length when we get there. So just to get it out of the way, this is pretty standard stuff. Our primary altimeter will be our RC3 Plus. We chose it just because it's what we went with last year, and it seemed to, at least in Andrew's testing, have some good results. As our backup altimeter, we're going to be using the Altimetrum Telemetrum. And so that has not only dual deploy ability, right? But it also has GPS. So that covers our COTS GPS and secondary altimeter, and that is permitted by the DTAG specifically, actually. And so to fly the altimetrum, we need a ham radio licensed operator. I think I said that in the right order. And we got one, Andrew, and actually we are in the progress. Me, Jonathan, and Abigail, our propulsion lead, are all going to be studying now that the government's open back up and we can get our FRNs.
So, going into the SRED flight computer system, this is going to be completely isolated from any of the COTS electronics, but it's still going to sit inside of the coupler. It's essentially it's essentially going to have similar components to what the COTS flight computers do, minus the energetic aspect. We're going to be running it on 2 18650 cells, and it's going to consist of microcontrollers, board, intelligent sensors, And there's also going to be a board for cameras, so we can get a recorded video feed, not live video, recorded specific. And then we're going to have a designated board housing our telemetry transmitter system, which we can then interpret on the ground. As far as hardware, we're going to be using a Yagi antenna on the ground for directional receiving by Hotgate. And then we have a software that we've been developing that interprets our telemetry data on the ground and displays it in visual format, allowing us to get data from the rocket in semi-real time and also record it to CSV files both on the rocket and on the ground stations and all that. As far as the structure of the inside of the coupler, we have our top and bottom bulkheads and then spacers that are going to be made out of, they're going to be 3D printed material to be determined either ASA or polycarbonate. And then per recommendation structures, we have 4 steel rods that are 4-inch each that run the length of the hull.
And so finally, in our avionics section, we've got our payload. So the sort of idea of this is that we have got a Geiger counter at the core. The sort of theory is that as we increase our altitude, we expect to see more ionizing radiation. We have less atmosphere above us to protect us from cosmic rays. And so we will invariably, hopefully, see a similar profile in radiation detection to our flight profile. And how we're doing this, of course, we've got a Geiger counter. That would be our radiation detector on the block diagram. This is going to be picked up by a microcontroller with independent sensors. So this thing should be able to operate with or without any of the COTS or astronautic flight computers, and that is to ensure system integrity in terms of, our flight computer goes down or we don't necessarily have the ability to correlate our data from the Geiger counter to our COTS optimization. We've just got an 18650 with a BMS powering the whole thing, and we've got dedicated storage, which we hope to be the same sort of thing as our astronautic flight computer for compatibility. And so when we go to recover this data, it's going to be given to us in CPM, that's clicks per minute. So if you've ever heard a Geiger counter, you know that it kind of clicks. And so what we're going to try and do is we're going to try and put it next to a known radiation source of a dedicated output in a format called Sievers, essentially. And we're going to try and scale that clicks per minute to the known, a Sievers measurement isotope, I guess. And hopefully we can recover that data in Sieverts, which actually gives it a nice unit.
Yeah, I was going to say, and just for clarification's sake, our payload is going to be mounted inside of the nose cone.
Yes.
Of the rocket.
Is there anything radio?
No. There's nothing radioactive in this payload. Right, and so to hold this thing together, of course, a Geiger counter has a Geiger 2, which is possibly glass. We are flying a hybrid, of course, and we expect a lot of vibration, aside from what you might expect in a regular, solid rocket. So we are going to use a system of dampeners. We've got, at least in the current thought, we've got a sort of foam surrounding it, right? And that's within some sort of, housing with I guess what would you call that? We'll call it a hard case. And then outside of that, we hope to have some sort of system of springs in order to make sure that we kind of dampen the larger vibrations. At least that's the theory. And so in order to make sure that this is actually a viable design, we plan to do testing. Testing, testing, testing. That's the name of the game. So we're going to be doing ground testing in terms of just shaking the darn thing, making sure it doesn't break, getting back that data, verifying the data, right? Because again, we can reference it to a known isotope. We're also in the fortunate position of having people that are going for their L2s and also L1s, and so we can flight test the thing. Not at altitude, but it's very, very valuable data nonetheless. Something that I don't have on here and that I'd like to see is that we hope to maybe take this thing up in a light commercial aircraft and also try and test it at altitude. That's kind of far off testing. So we're just trying to make sure that the data is good, that we don't break the Geiger tube during flight, and that we do see at least some sort of correlation as we take it up. Any questions? Oh, yes.
On flight. Are you concerned at all for 50 Beth? Are you concerned at all about the spring mass damper, like actually making a ton of noise with the accelerometers in there?
So we won't necessarily have any accelerometers on the payload itself. That's not necessarily something data that we need. Granted, I guess they're saying that it might produce noise for the accelerometers and the flight computers.
Yeah, like the aspect one.
That's something we hadn't considered, admittedly. And so we'll definitely look into that. Something that we could possibly do is work with dynamics and see if we can do some sort of analysis and see if there's any. I suppose it would probably be some sort of harmonic frequency that it might oscillate at to create that noise.
I would like to imagine that there's some way to reduce the noise through sensor fusion, because as part of our flight, we are going to include a magnetic field sensor. So the hope is that we can use the magnetic field sensor as an absolute heading, and then combine the accelerometer data with that to hopefully decrease the noise across the board.
Any other questions? No, we gotta get going, so that's good.
Howdy, I'm Abigail with the cost propulsion lead for guys. So this is our motor selection options. We chose to go with the 75mm contrail motor because that's what we worked with last year, so we already know that system, and to help our ground sports, we already know how to work that. So on the right, you can see our motor altitudes. Those are all the max altitudes of those other options. The SM11 did go the highest, but it has the longest burn time, which means it's too slow off the rail. So with like worse weather conditions with wind, it fluctuates by like 1,200 feet. We just thought that the better option was the N1491 because it only fluctuated by like 200 feet max. So we decided to go with it. This is just the thrust curve of the motor that we have. The burn time for this one is 3.4 seconds. The expected thrust to weight ratio is 4.51. And then the peak thrust is about 1,200 pounds. Average thrust is 280 pounds. And then on the right is the thrust curve, the certified one. So this is just a little overview of the N1491. We have our oxide is liquid nitrous oxide. The fuel is black smoke, higher emission rate fuel with an unspecified specific material. And then we do know it's a fuel grain, and all the fill lines run right through the fuel grain out to the combustion tube. Just a little breakdown of our motor. On the end, we have the graphite nozzle. It's a medium nozzle, and then the reloadable fuel grain with the fill and vent tubes. You can see it in closer view in I think the next slide. And then the nitrous oxide tank, and all this is encased in the metal tanks that they come in. With there's also overheads on both the connections for the nozzle and the chamber, and then they're all vented in. So this is a little close-up of the injector. There's the vent line goes right through the middle, and then it runs all the way out the combustion chamber. And then there's 2 crossover lines and then 2 fill lines with Pyrex pellets and then this is surged with wire, which is how we spark it. And our filling and plumbing, the rate is $120 per reload, valve, and then the next offsite costs, we're going off last year's. So the tank costs $126 from Paul, and then the approximate cost to fly based on what Tom Sanders told us is about $5, with about a 10-minute fill time and a 6-pound loaded mattress weight, and then the fill PSI from our motor is from 600 to 900 PSI. Lower, you obviously don't get any number. And then we have a few options for motor tension. We haven't nailed it down yet. But one of them is a bow tail or an air pack for bottom prevention. And then the top, the contrail motors have to come with threads on the top that you can eyeball in. So you can also screw them on the top and have top protection system. Any questions? Yes.
Guys, for check the first for feature maybe it's as a motor by working with friends.
Yeah, that's a different project. This is just a highlight. No questions.
Howdy.
Howdy.
Heard of a thing called deja vu. This year we're flying a hybrid, as you very well may know. And so not a lot of folks are necessarily familiar with hybrids. At least they're more familiar with solids. So just to give a very sort of top-down view of what ground support even is for, we need to make sure that the rocket is filled at a certain pressure with nitrous oxide, liquid nitrous oxide. And that presents several interesting engineering paradigms, we'll put it that way. So we have to get this, we can't preload the motor with the liquid. We can't necessarily be right next to the motor while it's filling because this is a very dangerous system at pressure. And that's still do have to be 1,500 feet away. We'll get to that. And we don't have to have a pump because the nitrous in the tank on the ground is pressurized by its own, nature. Okay. Goes up the tube in the tank on the ground, through our plumbing, into the tank on the rocket. That's just a very basic overview, right? And so not only do we have the sort of ignition system that you have for a solid motor, but we also have this. So this is a general overview of our system. It's heavily based on last year's system, just because we found it to be effective. We'll say that. So on the left here, we've got what we call Houston, colloquially. This is our human side ground support. This is where we press the buttons and we play with knobs and levers and dials and keys and whatnot. This is also where we get diagnostic feedback from the rocket side. We're at a distance of 1,500 feet. This is our tank that we're buying from Paul, and this is a general overview of what you might see at the rocket. So please, it's in that order. We've got the human side ground support, Houston. So this is our box from last year, and we're probably going to do something very similar this year. In essence, we have two big buttons for filling and purging the tank, and these are momentary push switches. As for the VTEC, we have to make sure that we have to hold this thing down while it's filling. We have to press the button to drain it all the way to make sure it drains. We've got two keys. So we've got one that enables fill and drain, and then we have one that enables firing with the help of the big red button. We're keeping the big red button. So that's the primary, it's mostly the primary functions that we really need. But this year, we're not so constrained for time or money, so we're going to have a little bit of shoot, yeah, you know what I'm looking for. We're adding a little bit more. We're a creature conference. So we'll have some sort of way while we press the fill button to see how long we fill how long we fill the tank. We should have a digital pressure gauge on the rocket side that will give us back some estimates about the pressure in the tank, and then we can use that in our sort of workflow as we're just determining whether or not the rocket is full. We'll have a thermocouple on the other side that we can see, and that's our basic fill detection. We've also got a buzzer, right? And this is just a last sort of train of defense, right? Where if we're ready to launch and the system's ready to launch, we need to make sure the operator knows. Just to say, this is the rocket side ground support. I'll try and be a little quicker. I'm kind of running out of time. But the general idea is that our rocket, of course, needs the liquid oxidizer, and we need to ignite the rocket. From Houston, we get signals sent in to control board. This interfaces directly with relays. Relays are used because we cannot directly interface a 12-volt system of valves with a 5-volt microcontroller. That's how we get a lot of magic smoke, as we call it in the industry. So we use those relays to control the valves as well as the igniter. The igniter's 24 volts, the valves are 12, so we've got 2 car batteries. And then on the nitrous side, we've got nitrous flowing into a pressure gauge. This is dedicated just to see what the pressure in the tank is, and that's something that Paul, the hydrates pad lead, wanted us to have, so we will. We've got our valves that control the flow. This allows us to not only pressurize, but also vent. So we can we'll have a separate valve for pressurization and venting, which allows us to do both. And I believe that's everything on this slide. The relays, I will say, so something that we're very keen on is safety with this system. And so the relays are one of the biggest points of failures that we're expecting. So we're going to have that system easily swappable. Now I can go to the next slide. So just a kind of a generalized overview for fill detection. Once the rocket's full, liquid oxidizer will start flowing out of the drain tube, and you will immediately sort of become gas, which is very cold, right? To detect that. We will have a black board as well behind I guess, the second line that's running out of the vent tube, and that way we can visually see downrange if we are venting off nitrous oxide. And we will have the digital pressure gauge, hopefully. That's something that we're still researching and developing. So the communication, we're going to go with a pretty similar system to last time. We will use 2.4 gigahertz as per the GTAG. We used an off-the-shelf module last year. We probably will do the same this year. It's just a lot easier, and we can reuse some of the code base. At 1,500 feet, 2.4 gigahertz is stretching it if you don't have sort of a high gain antenna. So we will be using it's called a CAN antenna. This is a monopole antenna with it's a circular waveguide. Doesn't really matter for this. The main thing is that we will have this verified and tested at a factor of safety distance of 2, which we will talk about at the next. So we plan to test at the Hearn launch site. It is an airport. It's very flat. It's very long, and we can do some of our preliminary testing there. This would allow us to do tests with factor of safety well past 2, but we're going to test for 2. And then after that, we plan to do this in a variety of extrema environments. So at further lengths, at different heights, ground clutter, you name it. We're going to make sure that this thing will have connection. And we will verify the independent systems. We hope to do a pressure gauge or a pressure test, but that is really far off right now. And then at Lone Star Cup, that would be a great way to test the entire system. So what happens if we have something go wrong? And we, again, safety is a really big thing for us. So we've got two separate ways to completely purge the system in case of a catastrophic failure. We can disconnect Houston from power. It will stop sending packets. Both will recognize, or I guess the rocket side will recognize that it no longer is receiving communication, and it will automatically vent everything that is within the rocket tank, but not the ground tank, because that's very expensive. Similarly, we plan to have an emergency stop button on a completely separate, isolated system, completely separate batteries, completely separate frequency. And in this way, we can ensure that we can remotely turn off the system, and that will also automatically purge the valves. And similarly, nothing ever goes right on the launch pad or at competition. So we will have all of the systems easily swappable at the launch site. So we'll be using standardized connectors that we can buy from hardware stores. We will also be making the components modular. So we will identify areas that are of high risk of failure, and we will make sure to bring at least another one. Are there any questions? Oh yeah, it was progress. Any Zoom questions? All right, well, we've reached the end of our video episode. This is our conclusions. The feedback form is the instruction form that you all should have access to now. Please put any questions, comments, concerns in there, anything at all. We're really looking for constructive criticism or just criticism. Yeah. And then there will be a kind of a general plot synopsis of what occurred. Not just sent out to the actual slides that we sent out, along with some of the questions we answered.
The recording of this entire PDR will be posted on YouTube for the next 24 hours.
Yes, the recording of the PDR will be posted on YouTube. You'll see it. Yeah, and thank you to our peoples. Yeah, thank you to all our sponsors for taking a chance on it. Yes, I want to give a thank you to all of y'all for coming out, and a special thank you to our sponsors for taking a chance on all of us. On business seat, so that yeah, it's just thank y'all to all of us for taking a chance on brand new rocket team. So yeah, it means a lot for us. Thank you.
If anybody has any more like all-encompassing questions about the PDR level, we still got about 1 minute left, so feel free to ask. And if you do that, it's good to do that.
You can come up here and we're on Zoom. We'll be watching Zoom. We'll be watching Zoom for additional.
Yes.
I heard earlier, like, don't want to lose weight. What was the motivation for that stuff?
Yes.
If y'all do need movements, I'm sure y'all can imagine that's the reason we didn't give less drag, so that might solve the problem altogether.
So yes, that's what we're looking at right now. Kind of the reason we're sitting at 4 fins because we can always cut 1 fin and drop down to 3. So we know this little extra 100 feet we can get into it. And to reiterate the question, it's about mass production. We're trying to go lightly and get it high.
And were y'all trying to characterize the vibrations to apply with that payload? And
we're trying to characterize the vibrations before we fly the payload because gyrokinetic sensors from some of our preliminary research are very prone to vibration caused error.
Yeah.
So we're trying to figure out how to reduce the vibration in the payload as much as possible.
Okay, I guess I'm just curious, like, if y'all are trying to characterize like what actual frequency you're gonna get, like I've done like very light research like on my form, but like from what I've seen, like the sampling rate for that is like it's so high that it's just like super expensive to do. Not sure, but
Do you know what that sampling rate is off the top of your head?
We try to do it for a bit because I know a lot of industry does like what's called vibration analysis on like PCBs to make sure like their ICs will break or anything. But it's just, yeah, it's only done in industry level because in order to get those frequencies, those actual like input vibrations, it's sensitive. Not sure.
We do our ANSYS software that we can look at. We do ANSYS as a sponsor. We can possibly use that for some of the vibration testing. I believe we actually do have some of that in their software suite. We've also got a LabJack. It's sponsored by LabJack. And I can't remember the sampling rate off the top of my head, but it was really good.
I think it's
100 kilohertz. I mean, that's not the fastest, but you know, it's still, I would say, probably would allow us to get some good data.
I agree. Answers is paying off. Like you can just get like an input PSP analysis. That's awesome. But I guess the problem that I guess we have is just like how do you get that input curve, right? So
We're doing our research into it.
yeah, that's cool.
The more data we can get on it, the better.
Yeah, I'm just curious, because I'm learning about like different materials and stuff for engineering, and what's it about fiber blocks that you guys do like? So like it's lightweight and strong. So for metals it's heavy. So most of the time you would use like, composites, which is lighter and it's strong. If you look at the aerospace industry, you're trying to figure out a way to combine metal atoms into the composites purely because we want it to be stronger. Yeah.
It's also very affordable.
It's cheaper than carbon fiber and doesn't block radio signals. Because carbon fiber blocks radio signals.
It's overall good material.
Where are you getting it?
We're buying it from Wow Rocketry.